All right, we'll get started. I just want to point out a couple of opportunities that I'm sure you've probably already heard about, but some of you are going to graduate this year, you hope. So assuming things go well, I'm sure you will. If you are about to graduate, you should really consider going to graduate school in this department or in many other universities. Many of the deadlines have passed, but you can still apply to UBC. You could do a master's degree in 16 to 24 months, but 8 to 12 months of coursework and 4 to 16 months of research, or you could just do all coursework, so on, to learn a lot more about many other areas of research in AI, all of these guys here, and could well pay off in terms of better employment opportunities, although there are lots out there now, but could be in a more researchy area. And you actually get paid to do this, which is amazing. You get paid to be a TA, or you get paid to do research, and so on. So if you're at all interested, apply. You don't have to accept if you get accepted, but if you don't apply, you won't be accepted. If you're not about to graduate, you should consider the Undergraduate Student Research Awards, NSERC Awards. Gives you an opportunity to sample academic research, again, in almost all areas of computer science. It's about 16 weeks. You get paid pretty well. And you probably have already heard lots about this, but you should email Juliana and talk to a potential sponsor as soon as possible. Unfortunately, I'm not a potential sponsor. I'm sort of taken at this point. Just want to bring those to your attention. Okay, so today we're going to talk about heuristic search in the proper sense. We've talked about best first search, which uses a heuristic, but we've shown that it's not necessarily complete, not necessarily optimal. It's almost too eager. And so we're going to kind of balance best first search with the cost of the search so far. Because you can think of best first search as sniffing towards the goal, and the closer it gets to the goal, the more it gets excited and keeps going down that track, right? But if some other path becomes more interesting, then it flips over to that one. Okay, but it's considering as sunk cost everything that it's already encountered on the path. Remember, this is only when it's going on in the agent's head. Okay, when it actually has to execute this plan in the real world, it'll have to start at the beginning and count the cost of every arc that it traverses. So it's by ignoring the sunk costs that best first search makes it too eager, too greedy. Okay, so we're going to balance that. First, as usual, we'll start with the lecture overview, recap of the lecture from last time. We're going to talk about searching with costs. We talked about finding routes in a two-dimensional world like this one, where we're trying to get to, say, Bucharest. And we've got all these different cities. We're going to start over here in Arad. Yes, it is. And there are many different search algorithms you could use for this. And of course, if you've encountered Dijkstra's algorithm, you'd say, oh, this is Dijkstra's algorithm. And yeah, basically it is. Least cost first, or lowest cost first search is basically Dijkstra's algorithm. Dijkstra's algorithm goes from a single node in a graph to all other nodes, finding the least cost path to all other nodes. We're only interested in a pair of nodes, but it's a simple difference. The advantage is that we can do better than Dijkstra's algorithm when we go beyond lowest cost first search, is what we're going to do today. And also you can see lowest cost first search as a generalization of breadth first search. And the way you implement it using the frontier is to implement the frontier as a priority queue of cost values, always maintaining the least cost path, say at the front, which you can pop off and check to see if you've reached a goal node on that path. If you have, you return it. Otherwise, you expand that last node on the path, giving you B new paths if there are B successors of that node, right? and then put them in the right place in the priority queue. Probably implemented using a heap. Okay, so we looked at completeness, and we realized that if we had a cycle of 0 negative costs, that would be a problem. So it's only complete if the arc costs are strictly positive, so that every time you cross an arc you encounter additional cost. And it's only optimal for non-negative. It's slightly different. We're allowing 0 arc costs for optimality. The reason you don't want non-negative is that you could get paid every time you traverse a negative cost is equal to a positive payment, and you'd be being paid every time you took an arc, and so you might want to just keep going around circles, around cycle until you accumulate lots of money without actually getting to the goal. That wouldn't be a good idea. We looked at the time and space complexity. We looked at this soft O or twiddle O, whatever you want to call it, where it's the same as big O notation, except we say, well, there could be a log b to the m. You can actually have log to the k of b to the m in here when you compare it with big O notation. So it's not strictly big O, but it's saying, well, that grows so slowly, we don't really care, compared to b to the m, which is guaranteed exponential. So again, I encourage you to look that up in Wikipedia look under big O, and you'll find everything you need to know about big O. Of course, that's all in our book, too. If you haven't encountered this big O notation, I hope you have, but if you haven't, there's a review of it, or even first time, in our book, and there's also, we don't do the soft O notation, but that's in Wikipedia. So if the arc costs are uniform, this is identical to breadth first search. Question?
I wonder if there's any algorithms can be optimal with negative arc costs?
With negative arc costs. That's a big question. It's a much bigger question than we're going to deal with in this course. If they're all negative, you can flip the signs and go for the maximum cost, right? I mean, there's a lot of subtlety there, and I'm not going to go into it. There's no clean theory, and there's a lot of optimization literature on that. It's in the operations research literature. For all the cases we'll consider, there'll be, arc costs will be positive, strictly positive, greater than epsilon, which is greater than 0. Any other questions? So then we started talking about search heuristics. Again, this is the idea of how close are you to the goal, getting warmer or colder. And so they apply to paths. You can think of the heuristic cost of a path, or the heuristic, because the estimate will only depend on the end node on the path. You can talk about the heuristic being applied to the node. Okay, so the search heuristic h of n, we talked about the difference between heuristics and algorithms, and they're not opposites of each other. You understand that? And then when we use them for search, we'll call them search heuristics. Search heuristic is an estimate of the cost, an estimate. It doesn't have to be an unbiased estimate. If you've taken statistics courses, you know about estimates, and you know that an ideal estimator is usually unbiased in that, on average, it's equal to the actual thing you're trying to estimate. This won't be true of ours. Typically, we're going to be dealing with biased estimators, and we're going to bias them low for reasons we'll see. So it's an estimate, not necessarily unbiased, of the cost of the optimal, that is cheapest, path from a node n to a goal node. So each node will have, no matter where it is in the search space, will have some value for this function h. Okay, so this one has h of n1, and this one has h of n2, this is h of n3. And we'll talk about how you get these heuristics, but in general it's kind of a black art. So we then used search heuristics in various ways, right? So we talked about how to get a search heuristic. The simplest case is when you're searching in the plane, in the Euclidean plane. And so, you know, if I want to go from there to there, the simplest way to do it would be to go cross country. Just assume there's a road between them, a straight road, right? That would give me an estimate. Any other route would take longer. So it's an estimate, it's an underestimate, typically, unless there is actually a straight road from start to goal. But it's an estimate, and we've actually published them over here on the right. So you can easily get it by just putting a ruler down on the graph, or you just take, the Euclidean distances between point 1 and point 2 is the square root of x1 minus x2 squared plus y1 minus y2 squared, right? So it's a right angle triangle we're dealing with. So that's how you get a heuristic in that case. And this is where the bias comes in. Let's call C of n the cost of the optimal path from a node n to any goal node. It's the shortest path from a node interior to the goal node. And we say a search heuristic h of n is admissible if h of n is less than or equal to c of n for all nodes. Not just for one node, but for every node in the entire graph. The heuristic has to underestimate or be equal to, could be an exact estimate, the cost, but it can't be overestimated. Okay? Because we want to be conservative. I.e. for all nodes is an underestimate of the cost to goal, right? So, is the straight line distance admissible? We went through this last time. Yes, it is, right? And the answer is simply the shortest distance between 2 points is a line. Any other distance will be longer than that, so it's admissible, right? Here's another example. Think about this one. So I now want to go to a new city, Urzini. Where's Urzini? Never heard of most of these places, but that's down here, right? You see it? Right there. So, and we want to go from any city to that city, but we just have the old straight line distances to Bucharest in the green box. So we say, well, how could we use these? We don't want to recompute shortest distance to this guy from everywhere. Let's see if we can use this old information. So what would be a possible heuristic? Well, you might say a possible heuristic is the straight line distance from there to there, and then the actual cost from there to there. So is this an admissible heuristic? What do you think? And what it means to be admissible. For every node, it has to be an underestimate or an exact estimate. Okay. See, mostly green. So most of you think it's no. So who would like to volunteer why it's not admissible? If you had green out. Yeah.
If you look at the city that's straight to the right of the goal,
This guy?
the distance from it to Bucharest and then back to the other one is going to be longer than the distance from it just to the goal.
So yeah, so the h of n for that city would be, according to that formula, would be, losing my point. If you were looking at h of n for this city, this says take the straight line distance from there to Bucharest and then go back to there. That is longer than the actual distance on a real road. Okay, so for that node, it's an overestimate. And that's all I need to know that it's inadmissible, because it has to be true for every node that the heuristic is less than or equal to the actual cost of getting from that node to a goal. So I just have to show one case where it's not the case, where it's not true. It is true for every, if this branch of the graph didn't exist, if we just cut out all these nodes over here and we're solving this same problem, it would be admissible, right? Because for every one of those, you've got to go through Bucharest to get to this guy. So this is, in fact, always an underestimate for all the cities on the left side of the graph, but not for the cities on the right side of the graph. Is that clear to everyone? So, again, always stop me. You've got time. Here's another nice problem. You might be solving this in a video game or something. You've got this robot that's moving around this grid world. Okay, here's the goal. The robot wants to eat some food or get some gold coins here, and it could start anywhere. and it needs to plan a route. It's an autonomous agent. The robot has to find a route from the start to goal location G on a grid with obstacles, and the only actions available to it are to move up, down, right, or go left if it can. Do any of those from tile to tile. No diagonal moves. And the cost will be the number of moves. That's roughly the energy the robot would use. So what would be a good heuristic estimator for that? For any start node, any possible start node, we want to estimate the cost without solving the problem. To say, if you solve the problem exactly using any algorithm and say, oh, that's the shortest path, that would be a good estimator for the cost of solving the problem, right? It's an exact estimate. However, you've already paid the price of solving the problem. So it doesn't, a good heuristic should be cheap to compute, okay? It should be very quick and cheap to compute. There's no point in making it's hard to compute as solving the original problem. Okay, so that's one thing. And secondly, it should be admissible. It should always be less than or equal to the actual cost. So any ideas for what you might do? Yeah? So.
Maybe the coordination of the initial point, and then you have the coordination of G, and then use Pythagorean theorem to find the distance between the two.
Okay, so if I were starting at any point, again, I could start starting here. I could just say, well, the Euclidean distance from there to there would be a good estimator. Yeah, and it would be an underestimate. Okay? We can do better than that, though, for this problem. I mean, I've shown barriers here, okay? These are walls. The robot can't go through these black walls. Yeah?
You could do like a straight line, but any straight line that goes through a wall at a big cost for that heuristic.
You could do that. How much cost would you add, though, to make sure?
More than the whole maze width.
Yeah, but then it wouldn't be necessarily an underestimate, right? You add too much. You've got to keep it an underestimate. Any other ideas? And imagine, one way to do it is imagine the walls aren't there, right? Solve that problem. How hard is it to solve that problem? Not that hard. Right? You just go down to the right row, and then you go across to the right column. Right? You don't need any fancy algorithm. You can just write it down. So that's the idea. You could use what we call the Manhattan distance. It's called the Manhattan distance because in Manhattan, all the avenues and roads are in a rectangular grid, and you can't walk diagonally across blocks. So, from here to here, the Manhattan distance is 1, 2, 3. Right? So the Manhattan distance from here would be 1, 2, 3, 4, 5, 6, which is the same as the Manhattan distance this way. It doesn't matter how you compute it, as long as you don't go backwards on yourself, you'll always end up with the same answer. So it's just the sum of the distances in the rows and the columns. So you just add up the absolute value of the difference in the row numbers and the column numbers. It's also known as the L1 distance, as opposed to L2, which is Euclidean distance, the square root of the sums of the squares of the differences, right? So the Manhattan distance, L1 distance to the goal G, sum of the absolute differences in their coordinates. Is that admissible for this problem? What do you think? So it has to be an estimate, it has to be an underestimate or exactly equal to it. So if there are no barriers, it's always exactly equal to it, because that's the solution when there are no barriers. Just go to the right row and then go to the right column, right? So it's a perfectly good estimator if there are no barriers. If you add in the barriers, what happens? The actual paths get longer. Thank you. So it's still an underestimate. No matter how many barriers you have, it can only get worse to solve the actual problem, because the Manhattan distance is assuming the barriers aren't a barrier. They're not a problem. You just go through any barrier, right? Whereas if I'm here, I can't do this. I can't get through there. That would be the Manhattan distance between that point and that point. So I have to go up and over and around and down. So it costs me more. Okay? So the answer is yes, that estimate is admissible. Okay? So I'm going through these examples because it's a question of intuition. So it's a bit of a black art for some problems to figure out heuristics, and I'm trying to give you some heuristics for finding heuristics. Okay? And the basic heuristic is to find a heuristic for a problem, find an exact solution to an easier problem. And that's what I just did. Okay? I said, take this robot navigation problem, throw away the barriers, get an exact solution to that. If I add in more constraints, more difficulties for the robot, it can only get worse for the robot. So my exact solution to the simple problem is a heuristic for the harder problem. Okay? And it's easier to compute. That's, again, a key characteristic of a heuristic. So let's consider the 8 puzzle. What would be a good heuristic for the 8 puzzle? We want to go from this configuration to that one. And there's a lot of different heuristics. There's no one heuristic for any problem. The closer a heuristic is to the actual cost, the better, without going over it, is the basic rule of thumb. And we can actually prove a theorem about that. In A star, the algorithm we're going to use where we'll use heuristics, we can prove that if one heuristic dominates another, that is always greater than or equal to another one, but closer to the actual cost, that heuristic will do less work. Okay, and if it's equal to the actual cost, it'll do exactly the minimum amount of work in computation in order to find the optimal path. Both will find exactly the same optimal path, but the better heuristic, the less work the computation has to do. Okay, so that'll come up later. So what would be a good heuristic for the 8 puzzle? Let's start with a pretty dumb one. Any ideas? A really dumb one. How dumb can it be? Say again? Manhattan distance for every block, every tile. Kind of expensive. I mean, we could, again, there's a trade-off here. Sometimes you can get a heuristic that's really quick and cheap, but it's not as good as one that's more expensive to compute. And then you might wonder which is the right one. Like a really cheap one would be just put this configuration on top of that one and count the number of tiles that are out of place, right? I mean, 7's already in the right place, right? But 3 is out of place. I guess there's nobody else in the right place. Is that right? Yeah. So the heuristic value would be 8. You've got to make at least that. If any tile is not in its right place, it's got to move at least once. So there's at least 8 moves required to get from there to there. Of course, it's going to be many, many greater than that. But that's a really quick and dirty answer to the minimum number of moves. Okay? So is it heuristic? Is this admissible? This should be a no-brainer. Yeah. It's a yellow. It's a yes. Clearly, right? I think this is the answer you were giving. Suppose you say, well, just because it's out of place doesn't mean that you can get there in one move. Maybe you should say it's the sum of the number of moves between each tile's current position and its goal position. So for 8, you know, it's 2 moves out of place. So for each one of these guys, each one of the 9, you add up how many moves it's got to make, right? And a tile can only move once per move. So instead of just saying for everyone out of place, we'll just count 1, we'll now count the number of moves it has to make to get in the right place. Right? We can't solve the puzzle this way because we're assuming things like, you know, tiles can go wherever they want. Right? Like they can just go through other tiles, et cetera, et cetera. But again, that's a simpler problem. So would you say that was admissible? Can you think of an example? In other words, when I ask you this question, you say, can I think of a case when this could cost more than the actual cost of the solution? If I can find any single case like that, it's inadmissible. Okay? So what do you think? Yes or no? Green or yellow? So I'm seeing some green. So does anyone want to Say why they think it's inadmissible? Yeah.
Well, if it's already solved.
Yeah, if it's already solved, then everything's in the right place. And that's the sum of the number of moves between each tile's current position and its goal. If it's solved, the current position is its goal position, right? These two are identical. So then the sum is 0. So it's an estimate of how much work to do, which is exactly 0. So it is an estimate. It's right on. It's exactly the true cost. Okay? So we need another example where it doesn't work. Yeah.
You would have to make note of how every move you make is moving 2 tiles. So one move would count as 2 of the sums you're making.
Well, I mean, strictly speaking, the way we're going to think about this is we're only moving the blank. So if you think about moving the blank, when I move the blank there, that's the same as moving the 4 there. So really there are only 8 tiles, not 9. The blank isn't a tile. And every time you move the blank, only 1 tile moves, right? So I don't think that this can be greater than the number of actual moves of the blank. Does that make sense to everyone now? If you had a green up, does that convince you? I think I convinced myself, but I'm fairly easy to convince sometimes. Okay, so here's, I say, a heuristic on how to construct heuristics. Identify a relaxed version of the problem where you've dropped one or more constraints. Then obviously the problem with fewer restrictions on the actions will have less work to do. So the solution to that problem will cost less than the solution to the original harder problem, right? Make sense? So and for each of these examples, we can say what we did. In the grid world, we assume the agent can go through walls, right? That's an easier problem to solve. You don't have to go around them. In the driver world, that is the Bucharest driving around Europe problem, we assume that you can always drive in a straight line from any node to any other node across country. You don't have to go on the real roads. So that makes the problem easier. In the H puzzle, number of misplaced tiles, assuming that the tiles can move everywhere, and the sum of moves between the current and goal position, it kind of assumes that tiles can occupy the same spot as others. You can very rarely actually realize that estimate. So this leads to an admissible heuristic because the problem only gets easier, right? So that's sort of hammering heuristics, and we know we need heuristics for best first search, and now we're going to use them in what's called A star. We'll talk about A star. A star is it's got a cool history. Again, Wikipedia is your friend. I just looked this up. I've been teaching this for a while. I never actually realized why it was called A star. It's called A star because in the original shaky robot at the Stanford Research Institute around 1960, they were trying to figure out ways for the robot to get around the lab and get the shortest path from one room to another room to where it was going to do its task, right? And so they started using Dijkstra's algorithm, shortest path. Seemed like a good thing to start with. Which someone else invented before Dijkstra, but Dijkstra's more famous. So Hart, Nilsson, and Raphael were 3 researchers working there, young researchers at SRI, Stanford Research Institute. And they said, well, we can add a little bit, and they sort of modified Dijkstra's algorithm with guessing directions to go in, and that was called A1. And then Hart came up with another modification. They called it A2. And then they came up with the final version, which they called A star. They call it star because of the Kleene star. It means for 0, 1 numbers of repetitions of an object from grammar theory. So in other words, they were covering all future versions of the algorithm A-N. I like that story. So here's A star. And what it does is it uses both the sunk costs of the costs so far to where you are at the end of the path you're currently considering expanding, and the guess of how far it is to go. That seems like a really smart idea. So the notation we'll use is we'll talk about heuristic cost of a path. Remember, the heuristic cost of a path is equal to the heuristic cost of the node at the end of the path, because you're only going from that node to the goal. You don't care what's behind you when you're just looking at the heuristic cost. Okay, so h of p, h of n are synonymous when n is at the end of p. This is the cost of the path so far, and we'll call this f of p is an estimate of the cost of all paths that start in path p and end up at a goal. Okay? So we write that out. Fp is an estimate of the cost of a path from the start to a goal via the path p, constrained to go along the path p. And so you can visualize it this way. We're going from a start node to some node n at the end of some path p. This is the path p. Then guess how much further you've got to go there. That's h of p. You know this cost. It's the sum of the arc costs along here. And we'll call f of p this plus this. Okay? And that's the only difference. Again, we use exactly the same search algorithm, the same generic algorithm with the frontier, except now we sort it by f of p instead of c of p, which is what least cost does, or h of p, which is what best first does. Right? So, A star combines elements of which two search algorithms? Treats the frontier as a priority queue ordered by f of n. It always chooses the path on the frontier with the lowest estimated distance from the start to a goal node constrained to go along that path, because we're including the cost so far as well as the guess of how far it is to go. Okay, so which two search algorithms are we combining here? So you need two cards to answer this one. Yeah, best first and least cost first. Okay, these two. Best first because you're using h of n. Least cost first because you're using the cost of the path so far, and you're just adding them up. That's how you combine them. Very simple. But it's amazingly efficient. And it's a good idea to run it a few times in AI space. So we'll start with a really simple example. So I've loaded the simple tree, and I want to solve it. Search options, I set search algorithm to A star. And I want to see the node heuristics, h of n. There they are. I don't know how whoever set this problem up got these, but that's what they guessed them to be. And I could also show the edge costs. There's all sorts of neat features, like there's a quiz. You can run quizzes for yourself here on what will the algorithm do next. It's a really good idea to use the quizzes in this applet. All sorts of things that I won't demo. And then I go to solve it and see how A star will try and find the yellow goal at the bottom there. So the heuristic value of the start node is 26. Here's the start node. The path cost so far is 0 because I'm at the start. H of s is 26. F of s is therefore 26. That's the path. So the frontier is always shown at the bottom of the screen. And if I expand that node, I've selected that path. I expand it to generate those two successors. I put those two successors and their paths on the frontier down here. And I now have a path cost for n1. Path cost is 9.9 because that's the edge cost, plus h of n1 gives you an f value of 35 for this node, and for n2 it's 27. So that's more promising. So if I find step again, it will treat that as the current node to expand and generate those two nodes which go on the frontier. And I've now got three paths in the frontier. Again, the f values are here. 28.5 is now lowest, so that's n5, this one. So it should be selected next. There it is. I generated the goal node, but I don't look at it to see if it's a goal node at this point. I put it on the frontier. You can see it down there. Right? It happens to have the lowest f value, so it will be taken off next. And when I take it off, I found that, and the total path cost is, whatever it is, 28.5. So notice the key thing, notice here is kind of the shape of the tree, right? The frontier is really penetrating deep towards the goal here because the heuristic costs are leading it there. But it's not overly greedy. It doesn't forget about the possibilities back there. As you go down, you'll be incurring more and more path costs, which may raise the cost of those paths on the frontier to be greater than the ones you've left behind. So you may have to go back and expand those a bit. Their costs will increase. F always increases monotonically as you go down because the heuristic costs you originally had in it are being replaced by the actual costs, which are greater than or equal to it. So if you look at the value, the F values as you go down the tree, you'll find that they slowly increase. It's an important property. So I could do a bunch of other examples. Why don't you do a bunch of other examples in your own time? But of course, it can get misled. I mean, this delivery robot is kind of misleading because yeah, it's too big. I don't want to do that one. It's too cluttered. I'm going to load another one. This is kind of smaller. The Vancouver neighborhood graph is kind of nice. So we've got Vancouver. There's UBC, and you want to get to Stanley Park. You're there, and you want to get there. Jericho Beach, Kerrisdale, Dunbar, Kitts Beach, downtown, Marpole, Burnaby, Surrey, Richmond Airport. Useful app. If you were in Google Maps trying to find a good transit route, you would use A*. They do use A*. So we could solve that one. And I think this uses shortest distance as the heuristic value on the nodes and the actual distance on the arcs. And then you could just solve it. So it's interesting to see how the frontier develops and how it's guided towards Stanley Park, but it's still checking out in Burnaby and Marpole. It hasn't got to Richmond yet before it found Stanley Park. Okay, so we've modified least cost first, which least cost first search least cost first search is always A* with a heuristic equal to 0. Okay, so least cost first is incredibly conservative. That's Dijkstra's algorithm. And what we're doing is being a little more adventurous without giving up the guarantee of finding the shortest path first. Okay, so we did that, we did that, we did that. Oh, here's our friend. I love this guy. I'm going to do it again. Except I'll give you a longer one this time. I love the way he almost lost it there. So that was part of an annual competition they had to solve this infinite Mario with various AI techniques. And that one did really well. Basically, it's just saying, at each point in time, it had to decide whether to jump and how high it should jump and so on. And all it's doing is using the information it sees on the screen. It doesn't see anything further than what you see off the screen. So again, complexity analysis of A star, back to the boring stuff. Worst case amount of time it'll take to run, expressed in terms of maximum length, maximum path length, and maximum forward branching ratio. What's the time complexity of A star? Worst case. Well, again, when you're looking for worst case time complexity, you say, well, what's the worst? How could it do really badly? Well, it could do really badly if it just behaved like breadth first. Because breadth first is A star. It's just got unit costs on the arcs and a heuristic function of 0 for every node. Right? And we know what the time complexity of A star of breadth first is. It's soft O, B to the n. Okay? So this is the yellow guy. I think most of you got that. That's what this says. Uniform costs and constant heuristic. H of n equal to 0. So we need to prove that A star is complete and it's optimal. In other words, it finds a solution if one exists. And when it finds a solution, it finds the optimal path to a goal first. Okay? But there are conditions on this. These are the conditions on this theorem. This theorem is known as the HNR Theorem, Hart-Nielsen-Raphael Theorem. It's quite a neat theorem, one of the first solid theorems in AI. Again, just because it's heuristic doesn't mean we can't prove things about it. We can prove that this algorithm is complete and optimal, provided the branching factor is finite, that is, every node has a fixed number of successors. It's bounded above by something called B. There's some number B such that no node has more successors than that. Whatever B is, as long as it's finite. The arc costs have to be greater than epsilon, which is greater than 0. So there has to be some fixed epsilon. This is different from saying that must be non-negative. Okay? Because there's some really neat corner cases where if, I don't know, suppose I had a path like this, cost of this one is 16, cost of this one is 8, cost of this one is 4, cost of this one is 2, cost of this one is 1, cost of this one is a half, cost of this one is a quarter, cost of this one is 1/8. In other words, at step n, the cost of step n is equal to 1 over 2 to the n or something like that. That doesn't satisfy the condition of this theorem because there's no epsilon. This path goes on forever. They just divide by 2 every time. Should be familiar to you. It's a Greek philosopher called Zeno. Said that no arrow can hit a target because every time if you shoot an arrow, first instant it gets halfway to the target, next instant it gets another halfway to the target, next instant another halfway to the target. So it takes an infinite number of steps, so clearly it can never reach the target. And they didn't understand the idea then that an infinite series could have a finite sum. But in this case, it'll really screw us up because A star could go down this path forever, and there might be some other path over here which actually has the goal on it, right? So that's why we require this arc costs greater than epsilon greater than 0, because no matter where epsilon is, as long as it's positive, if I take an infinite number of steps down here, eventually this arc cost will, the path cost will become greater than the path cost to goal, I'll come back and find this finite goal over here, okay? That's the intuition about why you need this condition on the theorem. And thirdly, of course, the h of n has to be admissible. It has to be an underestimate of the length of the shortest path from n to a goal node. So we talk about the property of the algorithm being admissibility. Okay, we talk about a heuristic function being admissible if it's always an underestimate or equal to the cost of a real path. And these properties of A star, completeness, optimality under these conditions, are known as the admissibility of A star. So don't confuse those two concepts. We're not going to prove this today. We'll prove it next time, Friday. You can read ahead in the book, and you should read ahead. Read the proof, try and understand it. It's a bit subtle. What we've learned today is how to construct heuristic functions for specific search problems. I've given you a heuristic for finding heuristic functions. You can define these search algorithms, and we will formally prove A star optimality next time. Thank you for your attention.